So it's a pleasure to introduce today Mathias Garny. He did his PhD in Heidelberg in 2008, has been then moving to TU in Munich, where he had a postdoc for 2 years, and has been now in Hamburg, DESY, and is now talking to us about the quantum treatment of leptogenesis. Please.
Okay, so thank you very much. So I will be talking about towards the quantum treatment of leptogenesis. I've been working on now for a couple of years. Well, to start with, I think I don't have to convince anyone here that we are in a very fortunate situation that we have quite a good understanding actually of the overall picture of cosmology, especially of course there are many really convincing hints towards the existence of a dark matter component on scales ranging from individual galaxies, galaxy clusters, up to the whole process of structure formation in the universe as a whole. So what I find very interesting in particular is now to see whether this picture that is emerging here from cosmology fits somehow together with the things that we know from particle physics. So in particular, I think it's very interesting to combine, for example, the question about the dark matter, and on the other hand, as you know, of course, there's now a lot of effort going on at the Large Hadron Collider to find maybe some new particles beyond the standard model of particle physics. And the most famous example here is, of course, the WIMP, the weakly interacting massive particle, that could really give a connection here between the dark matter that we produced thermally in the early universe, roughly with the correct abundance, and on the other hand, it could be possible to find some evidences of this at the LHC. And as you know, most of the searches are actually triggering on missing energy, which is directly related to the question that this could be a dark matter particle that is just escaping. So I think this is really a very rich field, also with a lot of observational prospects in the future. And I've also been working on this recently in the connection of indirect and direct detection of dark matter. But at the same time, I think there's also another very interesting connection that is maybe not as commonly emphasized. And this is another very basic property, if you like, about the universe as we observe it, that it has baryon asymmetry. And on the other hand, we also have, since more than a decade now, really firm evidence from neutrino physics that there is actually some physics, if you want to call it, beyond at least the minimal version of the standard model in the form of the observed neutrino oscillations. And as I will argue, actually, there's also could be a very interesting connection between these two phenomena that at the first place seem not to have much to do with each other. So in this talk, I mainly want to concentrate on this connection. So I will first briefly talk a little bit about the baryon or matter-antimatter asymmetry, and then about leptogenesis, which could provide this connection to neutrino physics. And then I will talk a little bit about the classical approach that has been used for this process, and then an approach that I have been working with based on a non-equilibrium quantum field theory. And then I will present an application of this approach to study the so-called resonant enhancement in leptogenesis. So to start with, I think it's an even much more basic observation than what we know about dark matter is that actually the universe that surrounds us, that we see, has this asymmetry. So basically a very basic observation is that we don't see any antimatter in appreciable amounts around us. So, I mean, apart from many arguments, the most direct arguments just come from some basic observations, like for example, in the cosmic rays, the fraction of antiprotons to protons is of the order of 10 to minus 4, even smaller at these energies, and this also the spectrum of these antiprotons is actually perfectly consistent with production as a secondary from spalations, so there's no hint and no need that there would be any appreciable amounts of antimatter around to explain this, and also more complex anti-nuclei have actually not been observed in the cosmic rays, what you would expect if you would have, like in our galaxy, really some appreciable amounts of antimatter. And there's also actually a much more stronger indirect method. So if you assume that like the interstellar medium, or also on larger scales, the intergalactic medium would consist of some mixture of matter and antimatter with some percentage, then you would expect actually a huge flux from the annihilation, mainly a gamma flux coming here from production of neutral pions in this energy range of a few hundred MeV. And actually this can be used to put really very stringent constraints on the possible fraction of antimatter on the scale of galaxies and also on the scale of galaxy clusters. So it's fair to say that there's more or less no doubt that the universe as we observe it consists of matter and not of antimatter. Now the question is why should we consider this as somehow interesting? And actually this was realized already now 80 years ago by Paul Dirac, who actually stated at the end of his Nobel lecture that if you accept the view of complete symmetry between positive and negative electric charge, so as far concerns the fundamental laws of nature, we must regard it as rather an accident that the Earth, and presumably the whole solar system, contains a preponderance of negative electrons and positive protons. So kind of the clash is that on the one hand the laws in nature seem to have this symmetry under charge conjugation, and on the other hand what we really observe has kind of on the first glance a maximal violation of the symmetry. So nowadays we know of course that there is actually a very small breaking of CP in the fundamental laws of nature, what was of course not known at this time. So this already kind of gives you a direction of thought whether this could have something to do with this asymmetry that we have around us. So for this it's important actually to quantify how large is this asymmetry, and a quantity that is invariant under the scaling of the cosmic expansion is the difference in the number density of baryons and antibaryons over the number density of photons. And this is very nicely determined actually by two different observations that refer to two very different temperature regimes of the universe. The most precise determination is via the baryon density in the cosmic microwave background, and also a consistent value appears from Big Bang nucleosynthesis at much higher energy scales. And if you compute this dimensionless number, then you find something actually of the order here of 10 to minus 10. So what does this number mean? This number means that if you would go back now in the history of the universe to a phase where the temperature is so large that you can actually have baryons and antibaryons in equilibrium, so above the mass, then you would expect to have really a thermal population of all standard model degrees of freedom particles and antiparticles. And this amount of asymmetry here would mean, or let's say an asymmetry of 10 to minus 10 would mean roughly that you have for 1 billion antiparticles in this plasma, you would have 1 billion and 1 particle. And so this seems really a peculiar initial condition. So one could ask, where could this possibly have come from? Of course, one logical possibility is that this is just some kind of initial condition that was just present for whatever reason. It's not possible really to really rule this out. But on the other hand, it also would contradict like the usual view that the cosmology underwent some phase of inflation in the early stages that left essentially just some empty space filled with the inflaton condensate. And also, of course, it would correspond really to an incredible amount of fine-tuning, if you like, to have this as an initial condition. So the other logical possibility is, if this was not an initial condition, then this asymmetry must have been created at some point, and this is called the process of baryogenesis. And already here, what looks very interesting is that since this is really only a very, very tiny asymmetry in the point of view of the early universe, the question to coming back to the point before, so could this be maybe related to the very tiny amount of CP violation that we see in the system of neutral K and B mesons? Now, to answer this question actually is not easy, but you can formulate very generally some conditions that the theory should fulfill in order to possibly create an asymmetry in a dynamical process. These are the famous Sakharov conditions from the late 60s. So obviously the theory must contain some process that violates baryon number, otherwise you will never be able to create a different number of baryons and antibaryons. Then it must contain this C and CP violation in order to have a different rate for the processes that create the baryons and the antibaryons. So otherwise, if this rate would be equal, you would create always in each process, and each charge conjugated process would have the same rate of occurring, and you would not end up with a net asymmetry. And the third condition is you also need a deviation from equilibrium, because otherwise each reaction and the backward reaction would be in detail balance, so you would always at each moment in time create and destroy the same number of particles and antiparticles. And as I said, in principle in the standard model of particle physics we know that we have some amount of CP violation coming from the CKN mixing. Then also above the temperature of the electric phase transitions there are the anomalous Falaron processes that in principle violate baryon number. But the question is, where could this deviation from thermal equilibrium come from? And there the process that could look most promising is actually the electric phase transition. Now the problem is that actually for a Higgs mass above roughly 80 GeV, this phase transition is not of first order, but is a crossover, and so it would not provide enough deviation from equilibrium to really create an asymmetry effectively. However, it turns out that these three conditions are fulfilled if we extend the standard model in a way to explain also the massive neutrinos. And this is now the part where the neutrino physics comes in. And then the process of creating this symmetry that was proposed here already in '86 is called leptogenesis. So, as I said, the basic motivation is that we have observed neutrino oscillations. So, both from the neutrinos coming from the sun and also from the reactor neutrinos and from the atmospheric neutrinos. And what this observation of neutrino oscillations is sensitive to is just the mass differences. So we don't know yet the absolute value of the neutrino mass and also not the sign of this mass difference here. but we know the energy scale at which these mass differences occur. And on the other hand, for the absolute value of the neutrino mass, there's an upper limit, the most direct upper limit here from the tritium decay of 2.2 electron volt. So what this tells us is at least two of the neutrinos are massive, because we have these two mass differences, and that the masses are, compared to all the other standard model particles, much smaller. So in the minimal version like of the standard model of particle physics, the neutrinos would be massless. But of course there's a simple way to introduce for the neutrinos also a mass. And if you look at the minimal version of the standard model, then it contains actually for the quarks, for all flavors, the left and the right-handed particles, and also for the charged leptons, the left and the right-handed ones. And for the neutrinos, it contains just the left-handed ones, so it is kind of a minimal extension to introduce also here these right-handed counterparts of the left-handed neutrinos. And if you do that, then you can write two additional terms to the standard model Lagrangian. So you can write a Yukawa coupling between the Higgs field, the leptons, and the right-handed neutrinos. So this is kind of the form of the usual Yukawa coupling term that you also have for all the other standard model species, and that give the mass via the Higgs mechanism. And then, since the right-handed neutrinos are total singlets, there is a unique term that can appear for them, and this is this Majorana mass term, where here is a new mass scale that is in principle not related to the expectation value of the Higgs field. So this is the reason is that the right-handed neutrinos are total singlets under the standard model gauge groups, and therefore you can write down this additional term. And now the famous seesaw mechanism, if you have both these terms to compute then the mass of the left-handed neutrinos, what you find is actually that this is given here by the square of the expectation value of the Higgs field divided by this scale of the right-handed neutrinos. And now the idea is that in principle this mass scale has nothing to do with the electroweak scale, so it could be much heavier. And in that case, kind of on the other side of the seesaw, you would get the observable neutrinos, which would be then much lighter than the typical electroweak scale, which is what is suggested by the neutrino oscillations. So now, on the other hand, for cosmology, this could mean that in this kind of extension of the standard model, we could really fulfill all the three Sakharov conditions. So the first Sakharov condition is kind of fulfilled indirectly. So we have this Majorana mass term here, which violates a lepton number by 2 units. And then via the Svaderon transitions at very high temperature, that would be converted, so there is a conversion between baryon and lepton number, only B minus L is conserved. So this would give us also a baryon violation at very high temperatures. And on the other hand, this lepton violation by 2 units that survives 2 hour scales that could be observable in the neutrino-less double beta decay and is of course actively searched for. On the other hand, there's a new source of CP violation, so this is completely analogous basically to the quark sector where we have the CKM matrix. Now here is a PMNS matrix that could also contain a complex phase, also because of the Majorana nature. Actually there are 2 additional phases that occur. And the third question is here actually, in my opinion, the most interesting one is the question, how could the deviation from equilibrium be realized? And here the idea is that in cosmology, if we have temperatures that are high enough to produce these heavy right-handed neutrinos, at some point the temperature drops below their mass and these neutrinos decouple from the bath. And in this process of the freeze out of these heavy neutrinos, there could be a deviation from equilibrium. And this is controlled by the ratio of the decay rate of these right-handed neutrinos over the Hubble expansion rate at the epoch when the temperature is comparable to their mass. Now you can do kind of a quick back of the envelope calculation what this number should be. So for the decay rate of the right-handed neutrinos, it should be proportional to the Yukawa coupling squared here, and the mass of the right-handed neutrinos with some phase space factor, and the expansion rate of the universe is just an expression with the degrees of freedom temperature squared over the Planck mass. Now, if you insert here as a temperature scale the mass of the right-handed neutrinos, then what you notice is that actually here you get a dependence of the Yukawa coupling squared divided by the mass of the right-handed neutrinos, and this is now very interesting because actually we have exactly the same parametric dependence here for the light neutrino masses. So this means also we have in principle here two unknowns, the Yukawa coupling and the mass of the right-handed neutrino, both depend in the same way on this combination, and this means in this right-hand side we can trade here the Yukawa coupling and the right-handed mass by the mass of the light neutrinos. And what then remains on the right-hand side is just the mass of the light neutrinos. And here an expression that involves just known quantities, so the expectation value of the Higgs field and the Newton constant in the form of the Planck mass, here the number of degrees of freedom. And if you just insert these quantities, then what just happens is that all these scales, if you combine them, they give you in the denominator roughly the scale of 1 milli-electron volt. And now this is quite remarkable in my opinion, because on the other hand we have seen from neutrino oscillations that actually the mass differences of the neutrinos are also at the order of, say, tens of milli-electron volt, and their total mass is certainly below 2 electron volt. So one would, with this kind of scale for the neutrino masses, one would naturally get here roughly a number of order 1. So this is why is this interesting. If this number would be much smaller than 1, you would have a too small decay rate of the neutrinos, which also gives you, on the other hand, the production rate of the neutrinos, you would never be able to produce them. If this number would be much larger than 1, then these neutrinos would just equilibrate and never deviate from equilibrium, and you couldn't produce your asymmetry. So essentially, you don't need exactly 1, but very roughly speaking, it shouldn't be too small or too large. And it seems that with the scale of neutrino oscillations that was of course not known at the time when leptogenesis was first proposed, this kind of prediction, if you like, from leptogenesis seems to go in the right direction now with the observation of neutrino oscillations. So one of the classic analysis of leptogenesis was done here by this gentleman, and the basic parameters that enter, this is here this effective light neutrino mass that I've also shown before, and on the other hand this is the mass of the right-handed neutrino, and you can see that if this effective light neutrino mass is of the order of milli-electron volt, as I had shown before, then actually in this huge range of the masses of the right-handed neutrino you can get the correct asymmetry produced by leptogenesis. Now if you go to values of this light neutrino mass that are too large or too small, then actually leptogenesis doesn't work as well anymore, as you either have no deviation from equilibrium or essentially no production of the neutrinos. And so if you then combine this, for example, with some other constraints from cosmology, like you wouldn't like to have a reading temperature that is too large, for example, to avoid overproduction of cavitinos, then you really would like to sit in a regime where this mass is more towards the minimum here, and then you are actually in this range here for the required value of the light effective neutrino mass. That seems to be really nicely compatible with the neutrino oscillations. So in a bit more detail, how does this leptogenesis really work to produce asymmetry? So the basic process is the decay of these right-handed neutrinos into lepton and Higgs pairs due to the Yukawa coupling. And at the same time, since they are Majorana particles, they can also decay into an antilepton, enter Higgs. so this is this violation of lepton number in this decay. But now, of course, if you just take the tree-level process, one depends on the Yukawa coupling and one on the complex conjugate of the Yukawa coupling, and you square this to get the rate, you get exactly the same rate. So to get a difference in the decay, you have to include here at least the first loop correction. And in that case, from the interference diagram of this tree level and this one loop vertex correction, for example, you can get actually a difference in the decay rate into leptons and antileptons, which is proportional to the CP violation in these Yukawa couplings, and also proportional here to the imaginary part of these loop diagrams. So apart from the vertex correction, there's also this wave function or self-energy correction that gives you a contribution. So what you have to combine is actually this interference of the tree and the loop process on the one hand side, which is kind of a quantum, has kind of a quantum nature, and on the other hand you know that the right-handed neutrinos also have to deviate from equilibrium to produce the asymmetry. So in a sense, both ingredients, some quantum ingredients and some non-equilibrium ingredients are really essential for leptogenesis. So the usual approach that is used then to calculate the generated asymmetry is basically to describe the leptons and antileptons in terms of their classical one-particle distribution functions at phase space, and just integrate over the phase space to get the total lepton number. And then the equation that is assumed for these one-particle distribution functions is the classical Boltzmann equation, where you have this energy conservation and then a gain term, so a neutrino decaying into lepton. This increases the number of leptons, and then here the Ross term. And so essentially what you assume immediately once you write down this equation is that you can describe the particle functions as a distribution of on-shell particles, and all the interactions are captured inside this matrix elements, which describe the transition from the asymptotic on-shell into the out states, typically computed here in vacuum. And so this was just the very simplest kind of equation you could write down. So of course there have been many refinements based on this framework of Boltzmann equations, which are of course extremely powerful. So for example, to include here these quantum statistical factors, which describe the Bose enhancement and Pauli blocking, to really solve them fully in momentum space, to get also the distribution of the right-handed neutrinos with respect to momentum, and also to include here in the computation of these various reaction rates thermal corrections. And well, then another important issue, flavor effects. So the right-hand neutrino can decay into a lepton and a Higgs. The lepton comes in 3 flavors, and so on and so forth. But on the other hand, actually, there are also some kind of generic issues with this description based on the classical Boltzmann equation. And one very well-known one is this double counting problem. So if you insert actually all the reactions for the decay of a right-hand neutrino into lepton or into anti-lepton, then you would write this as just some kind of tree-level matrix element, and then here this comes from the interference of the one loop, which gives you a small positive contribution for the decay into lepton and a small negative contribution for the decay into anti-lepton. So this is a CP asymmetry parameter. And then CPT tells you immediately that for the inverse process here, you would have to get a minus here, and for this here would have to be the same than this, so you would have to get a plus here. Now if you just make this very simple estimate of how the total lepton number would change, so it would increase if you produce a lepton, it would decrease if you produce an anti-lepton, and these decays are proportional to the number of the right-handed neutrinos, and then you have the corresponding inverse reactions, which are in principle proportional to the number of leptons and Higgs, and together combined they are equal to the number of neutrinos that you would have in equilibrium. And now if you just insert this simple estimate, then you find actually some spurious contribution here. Maybe you would expect that in equilibrium you have no production of an asymmetry, but what you find actually is that you have here a plus sign, so even in equilibrium, according to this naive estimate, you would produce an asymmetry. Now, it's very well known what is the origin of this apparent problem. The origin is actually a double counting problem between the decays and inverse decays of lepton and Higgs, and the scattering process where the neutrino just appears as some intermediate state that can in principle also be on shell. So if you like count here the rates of the inverse decays followed by a decay, in principle it's not possible to discriminate from a scattering that this neutrino is on shell. And so there's some, the usual procedure is to say, okay, we have to subtract this contribution here from the real intermediate state, and what this means is, in the simplest case, that you just replace the plus by a minus here. So you can do this a little bit more elaborate if you want to include like quantum statistics, thermal corrections, and so on. It quickly gets kind of a bit intriguing how to really extract this in the correct way, this real contribution. So the question is, could one also derive this maybe in a different way, not starting at the outset already from this classical set of Boltzmann equations? Then actually there's another process that can happen in leptogenesis, where the treatment based on the simplest version of the Boltzmann equation is difficult. And this is the so-called resonant enhancement. So you can write this CP variation parameter is the difference over the sum of the decay rates into leptons and antileptons. And this is then has then these two contributions from the vertex and from the self-energy correction. And actually from the latter one, you get a contribution to this CP parameter that scales in the denominator like the difference of the lightest and the next to lightest light in a neutrino. And the origin of this is in principle not difficult to understand. So imagine you have here this diagram, then this internal neutrino, if this is an N2, will give you this kind of propagator. And then if you set this momentum on shell for an initial N1 that is decaying, you immediately see that you should get some behavior like this. Now the question is, this would diverge in principle if the two masses are equal. This is of course not the physical behavior. So there was the question, how is this actually cut off? And actually there are, there have been lots of different calculations, especially starting in the 90s. And so this is kind of my attempt to summarize these calculations. Essentially, the B parameter is here proportional to the imaginary part of the certain combination of the couplings, which is proportional to the CP violation, and then this resonant enhancement term here. And this regulator A essentially regulates this singularity when the two masses get very close to each other. Now, there have been different expressions around in the literature of what this A should be. And in principle, this A is important because it gives you the maximal value that this function R can take. So this is directly related to the regulator A here. So in principle, it's also clear where this regulator should come from. So in principle, these are unstable particles. So this intermediate particle here has some finite width. So if you just insert here the Breit-Wigner approximation, you see that you somehow this width of this internal neutrino should come in. And on the other hand, you know also that the decaying particle is not strictly on shell because of the finite lifetime. And so you have potentially these two sources that cut off this singularity that appears here in the middle. Now the problem is that the whole process occurs out of equilibrium, and actually this maximal enhancement is precisely the case where you have a mass difference that is of the order of the decay width, so you have kind of these two Breit-Wigner resonances that start to overlap, and at the same time, to compute the asymmetry, you also want or you also have to describe the non-equilibrium properties of these particles accurately. And so, in this sense, to describe this resonant enhancement is also motivation to go beyond the usual semi-classical treatment. Now, the question is how to do this. And in principle, there are very powerful tools like the closed time path formalism and the Kadanoff and Bain equations. And so our goal was first actually to derive the kinetic equations, so not to use the Boltzmann equations as a starting point, but to derive them from some more fundamental equations, and then to kind of avoid this double counting problem that I described just before. And then in the second step to check really this resonant enhancement in this formalism, and then possibly also to include a number of effects that are not have not been looked at before. Now, actually, this has also been some activity in the recent years with a number of groups going in this direction. And okay, I will briefly describe what is the basic idea behind this. So somehow we have to replace this classical distribution function by some really quantum field theoretical object. And this object is typically taken as a two-point correlation function of the quantum fields. In particular, you can combine, or you can look at two combinations. One is the so-called statistical propagator here, which is the expectation value for fermions of the anticommutator of the two fields, and the spectral function, which is roughly speaking here the expectation value. Sorry, this is of course commutator anticommutator here. So for bosons it's the other way around. And okay, so what is roughly the meaning of these two functions? So if you want to go to the Boltzmann limit, in a sense, this would correspond to on-shell quasi-stable particles. So you would have a spectral function that is just peaked on the mass shell, and you would have a relation between the spectral function and the statistical propagator that is given by some fluctuation dissipation relation. So this is the usual relation that you have in thermal equilibrium. And now you assume that even out of equilibrium you have a similar relation, and this here would then you would then identify as the analog of the particle distribution function in the classical case. Now, if you want to go beyond this, then in general what you have is here some finite width that can, if you like, even depend on time in a complicated way. In principle, also the position of this peak here, the thermal mass, is something that in principle you should determine itself consistently from the properties of the system. And also, it's not necessary that you have really this relation out of equilibrium. Particularly, you can have these, if you have several species of the fields, you can have these off-diagonal correlators that somehow describe the coherence that you have between the transitions between the different species. And now the equations that are satisfied by these correlation functions, these are the famous Kadanoff and Bain equations. So basically these are just kind of Schwinger-Dyson equations for correlation functions that are out of equilibrium. And usually they are written not in the form of the Schwinger-Dyson equation that you know, because this is kind of impractical to go to momentum space if you have this dependence really on the two coordinates. And so the usual way to write them is to act here with this differential operator on the left, and on the right get then the convolution of the self-energy with the spectral function, with the statistical propagator and the spectral function. So essentially the upper equation, this encodes really the time evolution of this statistical propagator, which is more or less the analog of the Boltzmann equation. And then you get another set of equations here for the spectral function. And here what you compute, but at the same time have consistently is the evolution of the, if you like, the thermal mass and the width. In general, this can be an arbitrary function, here, the spectral function. And the feature is that you have on the right-hand side here this memory integrals. So in principle, these are non-Markovian equations. So at each step to go one step further into the future, you in principle have to know the whole past of the system. Now, if you want to apply this formalism to leptogenesis, then the most important observable is, of course, the lepton asymmetry. And here we also can find a nice generalization of the classical concept of the lepton asymmetry by looking at the current of the lepton symmetry, which is just given by this expectation value of the Noether current of the lepton symmetry. And immediately we see that here by the cyclic invariance we can express this as the trace of this two-point function. So if we know the full two-point function in principle, we know also the lepton current. And the lepton asymmetry is then simply the integral here over the zero component of the current. And we can derive an equation of motion, for example, by taking the time derivative. This will give us then here the divergence of the current. So if you have some interactions that violate lepton number, this is not zero. And we can put this divergence here onto acting onto the two-point function. And then we see that this is essentially just the left-hand side of our Kadanoff and Bain equation. So we can use now that this propagator here fulfills the Kadanoff and Bain equation. And then we get finally an equation of motion here for our lepton asymmetry, which contains also a memory integral over the past, and then the convolution of the self-energies with these different propagators. Essentially you get four terms, which more or less you can identify with these four processes of decay, inverse decay into particles and antiparticles. And now essentially the whole physics that you want to capture is encoded here into these self-energies. And so what are the relevant self-energies that you have to take into account to describe certain processes? So if you take here the one loop self-energy, for example, with the Higgs, the lepton and the Majorana neutrino, then this one loop self-energy would roughly give you the tree-level decay and inverse decay of the right-hand neutrino. So you can kind of roughly visualize this by thinking about what would be the possible cuts of this diagram. So this would give you essentially the tree-level decay and inverse decay amplitude squared. And then if you want to describe CP violation, you need these interference terms. So for the interference of the tree level and the vertex correction, you have to take this two-loop diagram. For the other contribution, you have to take this kind of nested two-loop diagram. And then you can see immediately that actually these diagrams permit also another cut, indicated here by these green lines. And they describe then here the interference of different S and T channels of the 2-to-2 scatterings. So the nice feature of this approach is that actually you get these processes really from one consistent, starting from one consistent diagram. So this contains the sum of all these contributions. So unlike in the Boltzmann approach, where you start with these contributions as separate processes and then try to combine them all in a consistent way, look for these subtle cancellations of onshore intermediate states and so on. Here you start really with everything together in one consistent expression. And then it's actually immediately easy to see that if you're in thermal equilibrium and you have the fluctuation dissipation relation, then it's fulfilled not only by the propagator but also by the self-energy. And then if you go back to this, have a look at this equation again, if you have this relation actually between the different F and ρ component, you can check easily that they cancel, and so automatically you get equations at least that don't have this feature of generating some spurious asymmetries. So this is something I was also working on a few years ago, and also other groups, as I mentioned. Now, actually, we also use this approach to estimate in the case that you don't have this resonance between for various neutrinos, but the dominance of one neutrino, the influence of certain thermal corrections that you now can incorporate into this propagators if you do not take the vacuum expressions, but the expressions in equilibrium. And so from one analysis, what we found here was that, so essentially what we have here is a change in the final asymmetry compared to what one would get using the vacuum matrix elements for different values of this washout parameter, which is essentially this light effective neutrino mass measured in units of milli-electron volt, or this gamma over h quantity. And then what we found is actually that roughly speaking, at zeroth order, the typical Boltzmann treatment gives a good answer, but you can get corrections here, for example, of the order of 20% in this case. So there one should be a bit cautious. What we assumed here is actually thermal initial conditions for the right-hand neutrinos. So this is important if you have here very small values. If you take here, for example, vacuum initial conditions, then you could get much larger corrections. But this regime is also not yet completely clear. And there's still some work to do to understand this. Okay, then briefly let me come now to the resonant enhancement. So what we want to consider here is actually two right-handed neutrinos with a mass that is very close by. So in principle there are three right-handed neutrinos, but we consider just the two that are nearly degenerate. So then our propagator would be a 2x2 matrix in flavor space, and here it's extremely important to keep track also of this off-diagonal components. And actually for the self-energies, in this case, in principle it's sufficient to use the one-loop self-energies, but what is important is that you keep here in this internal line of the self-energy really the fully resumed propagator. So what this means essentially is that you could imagine that you have here an arbitrary number of insertions of these self-energies into this line. So this is really a resumed propagator, and so it contains all the information also about the CP violation coming from this wave function correction, which is the dominant one in the resonant case. And then the step is to solve the Kadanoff-Embain equations for the system. So here we follow a treatment that was done in the hierarchical case, which is an approximation that allows to get really an analytic solution in this hierarchical case by treating lepton and Higgs as a thermal bath. So they have gauge interaction, so in principle they're much more close to thermal equilibrium. So in this sense is, I think, a well-motivated approximation. And now we looked at this for the resonant case, where you have to track really this whole matrix structure. And in general also you cannot find even with this assumption an analytic solution anymore. So here is one example of the result. So this is the time dependence of the asymmetry, of the lepton asymmetry normalized here to the value that you would get asymptotically in the Boltzmann case. So this is this dashed line would be just the Boltzmann treatment, and then depending here on the mass difference of the two neutrinos, if this mass difference is rather large, so factor 1.5 here, you would get just some oscillations around this Boltzmann treatment. And if the mass difference becomes smaller and smaller, then actually what happens is that these oscillations proportional to the mass difference squared, so they get a longer and longer frequency, but also the final value of the asymmetry is then somewhat suppressed here if the mass difference is relatively small compared to what you would predict in the Boltzmann framework. Now we try to estimate this also analytically, what happens here. So essentially in the Boltzmann case, this was this expression for the resonant enhancement with the different results for this regulator here. And actually what we found in a certain limit that is possible to do some analytic calculation, that in the Kadanoff-Bain case we get actually a very similar expression, and we find here for the regulator, so this was one of the terms that I had shown in the list in the beginning. So we could kind of confirm this calculation, but there's an important additional ingredient. Namely, we found also a time-dependent piece that comes precisely from this off-diagonal element, so from the oscillations. Now there's something interesting happening actually in the limit of rather large times. This coherent contribution actually effectively corresponds to changing or to multiplying here by a term that looks like this denominator in the numerator, and by a term that has actually here the sum of these terms in the denominator. So if you combine that, what you find at larger times is that actually you get something where you have here the sum of these two terms. So in contradiction to the difference that was found before. So what this actually means is that if you look at this in the space of the difference of the masses, and here is this resonant enhancement factor, then what you would predict is that you get the maximal enhancement when the mass difference is proportional to the difference of the two decay widths. So this would be this large maximum here. And in the case of the Kadanoff-Bain treatment, in the limit of very large times, you would find that the maximum is instead here at the sum of the width, and also the value at the maximum is quite different, and also you find this time-dependent behavior here. And then what we did in addition was to solve the system numerically for the case when this analytic approximation is not applicable, so when you have really large off-diagonal Yukawa couplings, which is the case that you are in the end also most interested in. And what we found here was that, well, roughly speaking, this analytic picture is robust, but the precise value of the enhancement can be changed a bit. Okay, so this brings me to the conclusions. So, as I argued, I think that it's very interesting to connect, on the one hand, what we have seen about neutrino oscillations, and on the other hand, the baryon asymmetry of the universe. And here I think really the remarkable equation is that the parameter that that controls the deviation from equilibrium in the freeze-out of these neutrinos is actually controlled here by the effective light neutrino mass, and if they are of the order of milli-electron volt, then this mechanism works nicely. And what I've shown you also is that one can describe here this as a quantum transfer process beyond the classical Boltzmann limit using Kadanoff and Bain equations. And what we found is that basically immediately you can resolve these double counting issues. You can include thermal corrections in a straightforward way. And we also concluded the resonant enhancement, and in particular the maximal enhancement, found that it's somewhat smaller compared to what was believed before in the Boltzmann approach. Okay, so thank you very much.
Thank you. Thanks for your interesting talk. Questions, please. Yes, Kimmo.
Can you go back a couple of slides? You had this. This is a different expression for A. Still on this one. I understood correctly. You say that at small times, this middle expression.
Yeah.
You say at large times you get to the lowest, but at small times it should still be the middle one. Did I understand that correctly?
Well, at large times you approach this expression.
Right, but first
at small times actually, well, also this coherent contribution is not small at small times.
Because I'm just what I would be getting at is that now if you have the middle expression and you are really pushing the m1 equals to m2 and the same width, then this is still divergent. So is this signaling that you couldn't use your method, or?
Well, okay, maybe this is a bit unfortunate way of writing it in the end. So what you can, I mean, what happens is that actually, I mean, this suppression of here compared to here, this is even stronger if you go to a bit earlier times. So if you look, for example, here, then you see that if you are here at the earlier times, then this R quantity is even smaller. So even if you go to this kind of doubly degenerate limit where the masses and the widths are equal, then at no point in the time evolution you would really see any divergence in this case.
Was it with this minus sign, this was the expression for uneasy one?
Yes, exactly.
So they were missing a term or something.
Well, I mean, essentially, I think in the one has to include this coherence of these oscillations in some way or another to get from this expression
That's what
to that one.
Any other questions?
Yeah, I have
Laura?
one. So exactly this coherence. So what sets the coherence in these cases? So are really the interaction of the n that you take into account, or in principle you could have also other interactions that could spoil the picture? I was thinking about gauge interaction or Yukawa's.
In principle, of course, you should take into account all these interactions, and well, but I mean, from the point of view of the Majorana neutrino, I mean, they are, I think, still, I mean, for them it's really the only interaction that takes place. So I think for them, this coherence shouldn't be influenced really by gauge interactions.
But for the flavor effect, also at the
But
end you
yeah,
didn't discuss
sure.
that
I mean,
very much. But
yeah, it could be really important because there you need the coherence really in the left-handed sector. There you have the gauge interaction is much more faster. So there, I would also expect that this could really be, could really have a big impact on the size of the flavor effects. But this kind of heavy flavor effects, I mean, there the right-hand neutrinos in a sense are much more cleaner, if you like.
So do you have a feeling for this sort of method of computing things, which looks quite clever? How difficult is it to generalize it also to scattering and annihilation processes and so on in your universe? I mean, you indicated that it's somehow sort of embedded, but in practice, how difficult would it be?
I think in practice it depends a bit really on the special feature of the problem that you are interested in. So I think in many cases it's possible to go to a kind of kinetic picture where some of the species you can assume very well that they are very close to on shell, and then you can use this as a starting point really for a consistent derivation of equations where you are then confident that you capture all these different, the interplay of these different contributions correctly. And in this case, I think it's very well possible to go also to quite a high complexity. So if you have a system where really all of these non-equilibrium effects play an important role at the same time, and you have to solve the full system, then it's more challenging. But also, I wouldn't say per se that it's impossible. Then typically you have to do the things numerically, but things are also evolving quite fast, and there's been also a lot of activity to really solve these equations in full beauty without essentially further approximations on a lattice. And I think also in this direction, at some point this could be applicable to really phenomenologically interesting situations.
I mean, if I remember well, you had the formula with the Planck mass.
Yes.
Where does it come from?
Oh, well, okay, this was just in the expansion rate of the universe. So it's not, it's just a convenient way to write
gravity.
Okay. So just a convenient way to write the Newton constant.
Mm.
I mean, it's just the you have the
Yeah, because you have
the
upper
Friedmann
constant.
equation where you just have the t to the 4 is equal to the density. Well, it's just because in particle physics one likes to think in terms of GeV.
Okay, if there are no further questions, then let's thank Mathias again.